Hello, my name is Apoorv Ranjan. I'm a master's student here at Purdue University, working in the Electric Propulsion and Plasma Laboratory under the supervision of Dr. Alexei Shasharan. We would like to take the opportunity in this video to introduce you to the concept of laser-induced plasmas. In order to do so, we will be dividing this video into three broader topics. First, we will be covering plasma basics, followed by microplasmas, and how to create these microplasmas inside the lab. And finally, we will look into the fundamentals of laser-induced plasmas.
Let's start by asking ourselves what a plasma is. You may have heard of plasma being referred to as the fourth state of matter. We can make matter transition from one state to another with the application of energy. Similarly, we can use this to create plasma. Let's take a sample of fixed gas in a closed system. We will supply the system with energy. Now the sample of gas will exert a certain pressure and have a specific temperature due to the molecular collisions inside the system. These collisions are mainly elastic collisions that change the molecule's speed and direction. However, if a collision has enough energy, then an ion may form by the ejection of an electron. So essentially, a plasma is made up of free electrons, ions, and neutral particles. This is a bit of a simplification, as a plasma is more than just an ionized gas, and a few conditions need to be met to initiate and sustain the plasma. Some examples of naturally occurring plasmas that you may have seen or heard of are things such as the northern lights, lightning, and even our sun is just a giant ball of plasma.
Unlike these naturally occurring forms of plasma, microplasmas can exist from the centimeter all the way down to the nanometer scale. These plasmas can also exist in a state that is not in thermodynamic equilibrium, which is to say that the electron temperature is significantly higher than the temperature of the ions and the neutral particles. In such cases, the plasma can be referred to as a cold plasma. And these cold plasmas, due to their properties, have a wide range of applicability, ranging from the biomedical field, where they're used for medical and dental purposes, to the food industry, where they're used for sanitation. In the aerospace industry, research is being done into how these can be used for aerodynamic flow control, and they even have applications in the manufacturing process for thin films. And so these microplasmas are extremely useful. So let us take a quick look at how these microplasmas can be generated inside a laboratory setting.
Scientists can take advantage of the few free electrons present in the gas. If an electric field is applied to the gas, the free electron will accelerate and gain kinetic energy. As a highly energetic electron collides with a neutral molecule, the molecule may ionize by ejecting an electron. If an electron is ejected, the new free electron quickly feels the electric field and also gains energy. This process is said to avalanche in this way and result in a cloud of electrons, ions, and neutral particles that is sustained as long as the electric field is present. The plasma in this case can be called quasi-neutral because even though it consists of ions and electrons, the positive and negative charges roughly cancel each other out.
Now that we've taken a quick look at microplasmas, let's move on and see how lasers can be used to ignite a plasma in gas.
It is possible to ignite a plasma in a gas using a laser. This is achieved by using a lens to focus the radiation. The gas particles around the focal length are ionized by the high-intensity radiation from the laser, thus generating a plasma. Now, the intensity of a laser is simply the power per unit area. In this case, the units used are watts per centimeter squared. The laser is capable of producing radiation with the intensities of 10 to the 9 all the way up to 10 to the 12 watts per centimeter squared. Let's take a closer look at the interaction between this radiation and matter in the gas. The laser interacts with electrons in the material by energy transfer and excitation. Free electrons absorb energy and accelerate, whereas bound electrons are excited to higher energy levels if laser photons match the bandgap energy of the atoms. Electron energy levels exist as discrete values that are specific to the gas species. If the atom or molecule is at the lowest possible energy level, it is said to be at its ground state, whereas the highest possible energy level, where the electron is still bound, represents the ionization threshold of the species. So when a photon from the laser hits the bound electron, it is capable of either transferring enough energy to ionize the molecule or an atom, or it is capable of exciting the electron to a higher energy state. However, there are cases where a single photon from the laser would be unable to ionize the atom or molecule. Instead, what may occur is a process called multiphoton ionization, which occurs when these valence electrons are ionized through the absorption of several photons simultaneously, which allow them to be excited to either virtual states or is capable of ionizing the atom or molecule. For example, let us assume that the wavelength is set to 800 nanometers and we are trying to ionize oxygen. So, for oxygen gas, the ionization energy is approximately 12 electron volts, and the photon energy corresponding to 800 nanometers is hc over lambda, where h is Planck's constant, and this is approximately 1.5 electron volts. And so, according to this calculation, we need approximately 8 photons to be absorbed to ionize the O2 gas. Another mechanism for photoionization that may occur using laser radiation is a process called tunneling ionization. As you may remember, the bound electron sits inside a potential well. In multiphoton ionization, we saw that the electron would gain energy by absorbing photons, and this allowed the electron to escape the potential well. However, if the laser has a high enough intensity, the potential well that the electron sits in is significantly perturbed by the laser field. This perturbation is simply adding to the linear function, which is a potential associated with the electric field of the laser. So if the intensity of the laser is higher, the slope is steeper, as seen in blue, and the potential barrier here is thinner, so it is easier for the electron to tunnel through it. Let us now analyze both mechanisms of photoionization together and understand the conditions for when we have tunneling ionization versus when we have multiphoton ionization. As we saw previously, tunneling ionization is associated with high laser intensities when the potential well is significantly perturbed by the laser field potential. Tunneling ionization can also be understood based on the frequency of the laser. It is important to understand that the overall perturbed potential that we drew was just an instantaneous view of the perturbed potential, and it changes with time following the oscillation of the electric field of the laser. And so, for tunneling ionization to happen, the electron has to be able to tunnel through the barrier before the field reverses. So the frequency of the laser is low enough. This linear potential oscillates back and forth slowly, and the electron has substantial time to pass through the barrier. The opposite case of this is multiphoton ionization. In multiphoton ionization, the frequency of the field is too fast, and the electron does not have enough time to tunnel through the thick barrier until the field direction and potential is reversed. So the electron is unable to tunnel through, and the only path for ionization is by absorbing multiple photons to escape the potential well. And so both these mechanisms that we've covered can be considered the extreme cases of the general process of nonlinear photoionization. This fact was understood by a Russian physicist named Leonid Keldysh in the 1960s. And he came up with something called the Keldysh parameter, which governs the transition between multiphoton ionization and tunneling ionization. And the Keldysh parameter is defined as the ratio between the laser frequency and the tunneling frequency. Essentially, what we see is that if the Keldysh parameter is high, multiphoton ionization is more probable, whereas if the Keldysh parameter is small, tunneling ionization is the more probable mechanism.
And that was our video introducing you to the concept of laser-induced plasmas. Thank you very much for watching and have a great day.